Chapter 1, Part 3, the history of the universe. Okay, the question is, or in fact, this is the question that we are all looking for. Um, how did we come to be? We're really looking for to understand, and this is the research that I'm also involved with. We wanted to know what initial conditions were we had that we ended up being alive on Earth, or that we ended up having enough stable conditions to grant us stable conditions, to grant us a sustainable situation that we can live on Earth. So we're looking to understand the birth of the universe. And this happens in um, 1930s. Hubble was observing galaxies, and he noticed that he thought that they are nebulas, meaning that he thought that some of these are just gas and dust. But then he understand that these are not just only gas and dust, these are individual galaxies. And then he noticed that these galaxies that he is observing, they are moving away from one another. Not only they're moving away from one another, they're also moving away from us. They're all redshifted. Their spectrum is shifted towards red, meaning that they are moving away from us. If we reverse this process, we understand that 5 billion years ago, all of these galaxies were closer to one another. 10 billion years ago, they were closer to one another. 14 billion years ago, they were the same point. Okay, so that this is the understanding that we have currently. And now we also have to consider that we have a cycle of the stars. When a star is born, after it runs out of the fuel, it will explode through a supernova. So all of the remaining material that exists inside the star will be part of a space. They'll randomly be distributed in the universe. So those are heavy elements, the elements that we can see in our body, the elements that exist on Earth. And then those are eventually will be part of another star or another planet. So in other words, we are star stuff. The materials that exist in us, that exist on Earth, it used to be part of another star before. That star died, exploded. Those heavy elements that was made inside the star. Remember, a star, the initial star, when you have, for example, what we have inside our sun, it's only hydrogen and helium. The heavier elements, heavier than hydrogen and helium, is being produced inside the star. So anything that exists in your body that you can see on Earth, oxygen, aluminum, iron, so on and so forth, they used to be part of another star before. That star died, and that caused these materials to be randomly distributed in the universe, happen to be part of another star or another planet or another moon. As I said, we are star stuff. So, and we understand all of these by observing the universe, making mathematical models, and understanding it. We understand that our own solar system was formed 4.6 billion years ago. So let's take a look at the lifetime, our lifetime as humans compared to the age of the universe, or what we call it in astronomy, we call it the cosmic calendar. This is a scale in which we compress the history of the universe into one full year. So from Big Bang all the way to now, from Big Bang all the way to now that you're watching this video, we have compressed this time to one full calendar year. Okay. Now, let's take a look. January 1st, which is the first day of the year, is where the Big Bang happened. February is where the Milky Way was formed, our galaxy. September 3rd, here is where the Earth formed. September 22nd is the early life in the early forms happen on to be formed on Earth. And December 17, December 26, and December 3rd. So most of the things that are current knowledge that we have, or the earliest knowledge that we have, is in December. Just imagine the full year, you're looking at the December, month of December. So the rise of the dinosaurs was in December 26th. On December 31st, at 11:58 p.m., just 2 minutes before midnight, the modern humans evolved. 25 seconds ago, 11 seconds ago, and so on. So, for example, the 11 seconds ago was the pyramid built. 1 second ago, Kepler and Galileo showed that the Earth orbits the sun, and right now. So it is a little bit challenging to some extent, or it's a little bit difficult to understand it, but you have to look at it in this way, that the whole 13.8 or 14 billion years of history of the universe, from Big Bang, which is the initial point, all the way to now, is being compressed into one full calendar year, where right now in the last second of December 31st, and the Big Bang is January 1st. So it's kind of a interesting to look that dinosaurs didn't even exist before December 26th, and you have a whole year before that. It's amazing. So let's take a look at the motion of the Earth. So contrary to our perspective, we are not sitting still. Right now that you're watching this video and I'm recording this, for example, we think that we are just staying still, everything is stable, nothing is moving, but we are moving with with Earth, and Earth is moving in 7 different ways, okay? And it's surprisingly very, very fast, but we don't feel it. And the reason behind this is, compared to Earth, our size is really, really small, and you have Newton's laws of motion governing the way that we feel about the motion of the Earth. So if you're staying all the way on top of the North Pole, the tip right there, top of this ball, you will experiencing 0 kilometers per hour of rotational speed. If you move a little bit further down, maybe around the border of Canada, United States, you're feeling about 1,100 kilometers per hour. This is the rotational velocity, or rotational speed of Earth rotating around itself, causing the day and night. If you were in the equator, you're feeling about 1,670 kilometers per hour. So Earth rotates around its axis once every 24 hours, or once every full day. One full day will take 24 hours to do one rotation. And if I ask you, with what the speed do you feel that rotation, you should say, we don't feel that rotation, but it also depends on, because we are leaving in it, okay? But it also depends on where you are at on Earth. If you are in the equator, that would be the answer. If you are somewhere north, that would be this. If you're on a north or south pole, you will feel zero. There's no zero, because you're technically rotating around yourself. There is no distance to the center. So the reason that in the equator, somebody in the equator is experiencing more speed is because this distance is higher or bigger compared to this distance. And since there's no distance for this guy, there is no velocity. This is technically looking like a merry-go-round thing, where if you're further away, you're feeling more acceleration and you're feeling more velocity, versus if you move to the center, you're just technically rotating around yourself with no velocity, if that makes any sense. So not only that, so this type of motion, it takes about 24 hours, once every 24 hours. We also have another motion for Earth, which is Earth rotating around the sun. So which takes one full year, 365 days, okay? So at an average distance of 1 AU, and every time that you see 1 AU, okay, AU stands for astronomical unit, and is about 93 million miles, 150 million kilometers, or 93 million miles. AU is astronomical unit. It's the average separation or average distance from Earth to Sun. Okay, and something that I would like to indicate here, and we'll talk about this later on in later chapters, but Earth is tilted with respect to this line. So its axis is tilted 23 and a half degrees with respect to this line right here. Okay, and this is towards the Polaris, and Polaris is where the we call the polar star as well. So it is taking one full year for this motion to happen, starting from this point, going all the way around the sun, coming back to the same point. Okay, and this motion is actually pretty fast. The speed for this motion is 107,000 kilometers per hour. So as we are moving around the sun with an average separation of 1 AU, in order for us to rotate one full rotation in 365 days or 1 year, we have to have 107,000 kilometers per hour of a speed. Not only that, we are also moving in random direction. Our sun moves in relatively random directions compared to the other stars in the neighborhood. Okay, so of a typical relative speed of about 70,000 kilometers per hour. So our solar system, so we are bound to the star, we are bound to the sun, okay, because of the gravity. So anywhere it goes, we kind of go with it, right? But our sun moves in random directions or in random relative directions compared to the other stars with an average speed of about 70,000 kilometers. But what if that's happening, why we don't really see anything? Why the stars that appears every night are still in the same spot every night? These stars are so far away that we cannot easily notice this type of motion. Remember, the the closest star to us is Alpha Centauri, which is 4 light years away. And we have billions of the stars in the night sky. So it is it is um, it takes quite a long time for us to understand that motion. Our sun or our solar system orbits the galaxy, our Milky Way, every 230 million years. So just like Earth rotating around sun, our sun is rotating around the center of galaxy, and that rotation takes 230 million years. Okay, the distance of where we are to the center of galaxy, which is just a black hole, is 27,000 light years. Okay, 27,000 light years. Now, this is an unbelievable distance, and this is an unbelievable rotation. If you wanted to rotate with that timing, you need to have 800,000 kilometers per hour of a speed. Okay, I don't want you to remember these numbers. I don't remember these numbers. Every time that I get to these points, I just read them. You don't need to remember these numbers, but you need to know that these type of motions exist. There is one Earth Earth rotates um, around itself. Earth also rotates around the sun. Our sun, with respect to the local cluster of the stars, moves in a random direction. But not only that, it also moving around the center of our galaxy. Our galaxy in the local group moves with respect to the other galaxies in the same local group. And they are interacting with one another through gravity. And at the same time, everything is expanding. At the same time, the universe is expanding because after the Big Bang, everything is expanding with the same rate in all directions. So how many motions we have? 1, 2, 3, 4, 5, 6. I want to add another one to it. So if I ask you how many motions we have, you have to say 7 motions. What's that? Remember this? Right here, the 23 and a half degrees. This 23 and a half degrees, we do one full rotation around the axis. Okay, one full rotation around this axis. Which axis? This axis. Okay, so the axis of the Earth, which is tilted, the axis of the Earth, which is tilted 23 degrees, it does one full rotation like that every 27,000 years. That's another motion that we have. We don't experience it because it's very, very super slow. So in other words, um, right now the axis of Earth is towards Polaris, right? This is the Polaris star that we see towards the northern pole. 13,000 years from now, the axis is tilted. The axis has moved to here. So another star will be our polar star, will be towards the North Pole, because this axis is moving every 27,000 years. So if it's right here towards the Polaris right now, 27,000 years from now will be in the exact same direction again. So that's another motion that Earth experiences. All right. Now, in order to understand the expansion after the Big Bang that we were talking about, just imagine or think about a raisin cake, okay? So this is before baking, before we put it in the oven. Each of these raisins, or local raisin, let's call them, they are about 1 centimeter apart. So raisin number 1 right here, and raisin number 3, they're 2 centimeters apart. So 1 centimeter and 2 centimeters right here. After 1 hour of baking, they're each 3 centimeters apart. In other words, after 1 hour of baking, number 2 is about 3 centimeters away from number 1, and number 3 is 6 centimeters away from number 1. So the further away you are, the faster you are moving. Okay? The further away you are, the fastest you are moving. Okay, so let's take a look. What do I mean by that? Raisin number 2 and raisin number 1, they were 1 centimeter apart. What are they now? They are 3 centimeters apart. Raisin number 3 and raisin number 1, they were 2 centimeters apart. What are they right now? 6 centimeters apart. So the further you are, the fastest you're moving. And this is true for our universe as well. After the Big Bang, the further you are, the faster you're moving. And that's why Hubble found out, and the Hubble Space Telescope actually confirmed this, that the galaxies are moving away from one another, and the further they are from one another, or the further they are from us, they're moving faster. So Hubble discovered that all galaxies outside our local group are moving away from us. The more distance the galaxy, the faster it is racing away. I talked about this. So this would be our end of chapter 1, the modern view of the universe. Let me know if you have any questions. You can email me or you can leave a comment, whichever way that you're more comfortable. Okay, end of chapter 1. Talk to you guys soon.